Check. Okay.
All right. Hi, everyone. I'm Mike Grudic. I'm a Hubble Fellow at Carnegie Observatories. And today I want to talk about what my best educated guess is for what the IMF might have looked like at Z of 10. So the IMF is obviously extremely important. If we want to know anything about the physical properties of any sort of system observed through integrated stellar light, you need to do a photometry model, and the first input into that model is the IMF. Then you assume a star formation history, stellar evolution, you get some prediction, then you make some inference about all these things we want to know about galaxies, masses, ages, star formation rates, reddenings, etc. So the question is, you're doing this, you see something you don't understand, do you press the IMF button? Do you vary the IMF in your model? Well, it's not something to be taken lightly. There's something that I've seen called Dave's theorem, which is that all problems in extragalactic astrophysics can be solved by an appropriate choice of the IMF, right? So that doesn't mean that that's actually the solution to all the problems, so you have to be careful. You need extreme caution. But I want to talk about what do the observations and, more recently, the simulations have to say about the issue. So just to kind of situate you with where the observations are at right now, this is a compilation plot of IMF slopes measured in all sorts of different systems in the local group. So horizontal bars are the mass range, and vertical bars are the error bars. And we see that there is definitely a great degree of regularity in the IMF. They all do seem to line up along a certain locus. However, while some of the variance we're seeing here is probably systematic, it's unlikely that all of it is. And in particular, I'd like to point out that the places where we measure fairly top-heavy IMFs tend to be in the more extreme regions of the local group, so either 30 Doradus or the galactic center. So that's kind of interesting. So just to get situated for the sorts of conditions I'm thinking about with the Z of 10 galaxies based on the observations, to give some quick numbers, I'd say metallicity is in the 1 to 10% range, reasonable. Sigma SFR, radiation energy, density, and pressure should also all roughly be proportional, and they should roughly be about 10,000 times what we see in the solar neighborhood, which interestingly is about 100 times more than the galactic center. So, essentially, if things are already looking kind of weird in the galactic center, then they might be crazy in the high redshift universe. It's also worth pointing out that the gas is definitely warmer. That's something we know for sure because it can't cool much below the CMB temperature, which is about 30 Kelvin at this redshift. And people have looked at the effect of just varying the CMB temperature on the IMF. So these are experiments with hydrodynamics and all of the relevant cooling physics. And generally what has been found is that, as they crank up the CMB, they find that the IMF gets less and less bottom heavy and it turns more bottom light. So it appears that the CMB does have some effect on the IMF. Part of what they're seeing might have something to do with the opacity limit. This is an old argument, an oldie but a goodie. Essentially, gas cannot collapse isothermally forever, right? Because its cooling radiation emitted from dust will eventually be trapped, and then it'll evolve quasi-adiabatically, and the gene's mass will start going up. So that kind of sets how small of a fragment you can really make. Recently, I kind of worked this out across parameter space in a little bit more detail than had been done before. And what I found was actually that this minimum gene's mass due to the opacity limit is larger both at lower metallicity and in more intense radiation fields. So based on the sort of thermal processes dictating fragmentation, we can say probably that the IMF could have been bottom light at high Z, but we really care about the massive stars, don't we? Because those are the things that are actually emitting all of this light that's ending up in the telescope. So to deal with the high mass end of the IMF, you basically have to account for the entire kitchen sink of physics. So that's what we do with the Starforge simulations. These are numerical MHD simulations with cooling chemistry, MHD, and body dynamics. We follow individual stars forming and accreting. And crucially, we account for all of the different types of dynamically important stellar feedback. So jets, winds, supernovae, and radiation. And we put all of these into one nasty simulation and see what comes out. So these are still kind of new, so I'll show you just sort of what these simulations look like. So this is an example of a kind of model of a solar neighborhood cloud. So 10 parsec radius, 20,000 solar masses in the cloud. We give it some initial turbulence. We let it go. It undergoes this sort of turbulent collapse where you have these filaments and sheets and hubs forming, kind of like CDM, but of course it's gas. It's not dark matter. And eventually you get these gravitationally unstable cores forming, collapsing into individual stars. These individual stars accrete. They give off feedback in the form of jets and radiation powered by accretion and fusion. And eventually some of the lucky ones of these stars will, of course, get more mass than others. They'll go on to become massive stars, and they'll have all of this radiation and winds that blow out the gas around them. And while this is all going on, the star cluster is assembling, and more massive stars are forming, until eventually feedback has reached a point that it's strong enough to start blowing the cloud apart. So we sort of start opening up a cavity around the star cluster, and the cloud starts expanding. At this point, the star formation is winding down, and eventually the cloud expands more, the cavity opens up, and the first supernova goes off, and that sort of puts the final nail in the coffin for star formation in this cloud. So essentially what we've done here is simulate star formation from start to finish, accounting for all of the feedback processes, and we can see what comes out in the end. So what do we have to say about the IMF? Well, the simplest model we tried to start out was just isothermal gas at 10 Kelvin plus magnetic fields plus gravity. And that gave us this sort of weird top-heavy thing. It was very easy to make very massive stars. Accounting for more detailed cooling physics didn't make it any better. Still just very easy to make very massive stars in very normal Milky Way clouds. So clearly that's off. Protostellar jet feedback is actually very important for regulating the IMF. Because it's always there, whether it's high or low mass star formation, and it's always quite powerful. But still, adding protostellar jets, we still form multi-hundred solar mass stars. But then once you add all of the physics, including the radiation and the winds that are disrupting the cloud, then you get something that looks quite reasonable. And I wondered what the deal was with this top end of the IMF, the most maximum star we see in these clusters. Is this a size of sample effect just from sampling a power law, or is it a real cutoff? So I actually ran 100 of these things, and I stacked their IMF, and I found that, yes, there is an actual cutoff. You don't just sample further up the power law if you run more of these. So this cutoff is real, it's physical, it's set by feedback physics, as you can see by comparing with the DASH model here, which has no feedback, forms very massive stars. And it also scales with the bulk properties of the host cloud forming the star cluster, which we can see by comparing with this one model in burgundy here, which is a 10 times more massive cloud. And that one cloud formed maximum stellar mass twice that of the entire sample of lower mass clouds. And if you think about it, this is actually kind of the most natural thing in the world at a back of the envelope level. You can ask, how much feedback do you need to disrupt a cloud within one free fall time? Given the cloud's mass and its surface density. And for the different types of feedback, well, for momentum feedback, like radiation or radiatively efficient winds, you require a momentum rate that's proportional to the product of mass and surface density. For energy feedback, it's proportional, again, to this product of mass and surface density. Photoionization, qualitatively similar thing. So essentially, whatever kind of feedback you want, it's easier to make more massive stars in both denser and more massive clouds, and without blowing the whole cloud apart. So, it's not crazy. But this is back of the envelope. So what do we see in Z of 10 conditions? So this is very preliminary, but we have been firing off a suite of clouds that are more appropriate for Z of 10. So this is using our turb sphere setup. It's a little more realistic, where we pre-stir the cloud and develop turbulence before we switch on gravity. We have a background radiation field that's 10,000 times what is seen in the solar neighborhood, so sort of consistent with the sigma SFR that people are seeing. Again, 20,000 solar masses, surface density of 10 to the 4 solar mass per square parsec. And what we find so far, this simulation is not done, is that the maximum stellar mass that formed in this simulation is 283 solar masses. The high mass slope is minus 0.8 versus the saltpeter minus 1.35. So it is quite top heavy. If you ask what the UV light to mass ratio is, right now, essentially at zero age, it's about 10 times that of a standard IMF. If you were to integrate over the cluster's lifetime, you'd get about 3 times more UV photons out of this thing. And it's still running, so we're going to run it all the way to cloud disruption and see what we get. And we're also running a broader suite of different conditions in this sort of setup. So, to summarize, when you're studying these high redshift things, should you press the IMF button? My answer is maybe. Keep an open mind about the IMF. Based on what we've seen on the theoretical and simulation side with StarForge, we find that massive star formation is feedback regulated, and feedback is inevitably less effective in Z of 10 conditions, so that would basically make it a lot easier to make massive stars. But there are, of course, tons and tons of caveats for these sorts of simulations. It's still early days. So I'd say, consider my qualitative picture, and I'll be very careful and give you a more quantitative picture later. But I'd also like to point out that these same physics, I think, also make the enhanced star formation efficiency and bursty star formation scenarios very plausible. So I think in general, just these sort of small-scale coupled dynamics of feedback and the IMF may well prove to be very important for understanding what's going on at high redshift. Thank you.
Thank you, Mike. So wonderful simulations. Right, okay, so I'm going to take the chair's advantage to ask a question myself first. You have included so much of physics. Do you think at these redshifts and densities, cosmic reheating would be important?
So that's a fair point because, yeah, the star formation surface density is 10,000 times more than the solar neighborhood. You're also going to get more cosmic rays. When you work it out, actually, you find that the way the cosmic rays scale is not quite the same. And I'd actually expect them to scale up about a factor of 100 compared to the solar neighborhood versus 10,000. This is based on Mark Krumholtz's work. So definitely the cosmic ray ionization is way more intense. But based on my experiments, it hasn't been like the key factor for setting the thermal structure of the gas.
Okay, thanks.
Thank you, Mike. 2 quick questions. The first is a low redshift, given the fact that you are not forming stars more massive than 30, would you be worried by the fact that in that case you would not form black holes anymore? First question. The second, when you go to high redshift, now you're finding 283 solar masses as a maximum mass of the star, but in the context of POP3 stars, they could never go beyond 40 or 50 solar masses. This is results from the Japanese group. So can you comment on all these points?
Yeah, so regarding the first question, so we do actually form stars more massive than 30 in low redshift conditions. Again, this depends on the cloud properties. This is showing you two points in parameter space. These ones on top are 2,000 solar mass clouds, so actually very low mass clusters, like 100 solar masses. But in general, we do find that across the model space, we do reproduce the entire observed range of stellar masses. Regarding POP3, so you alluded to a result, if I understand correctly, where it's difficult to form things more massive than like 40 or 50. Yeah, that's interesting. The conditions they consider are very different from the ones I'm considering, like metal pristine, mini halos, right? So that might have something to do with it. Definitely, initial conditions matter a lot. That's one of the things we're learning.
Yeah, thanks, Mike. Pratik Gandhi at UC Davis. So it's regarding the second point you made in your summary slide about the same suppressed feedback in these conditions might also lead to enhanced star formation efficiency and bursty star formation. I think maybe this is me just thinking about galaxy-wide properties, but I would think that less effective feedback would lead to less bursty star formation.
I don't necessarily agree with that. I think an important part of the bursty star formation story and what kind of differentiates models where it happens versus where it doesn't is that in order to get this kind of blowout, you need star formation to be able to run away locally on sort of small scales and not know anything about the balance on larger scales. So you kind of need to make this star cluster efficiently, and then you get that supernova feedback, and that blows stuff out. So I think locally high star formation efficiency can be quite important for bursty star formation, potentially.
Quick comment, Jerry?
Just a quick final question while you're getting set up for the next speaker. I realize that you're focusing on high redshift and high density, but somewhere not quite so high as redshift 10 probably, massive stars form, low mass stars form in high density regions that today are the centers of the massive elliptical galaxies. And there's strong evidence, I think, that those are bottom heavy. Do your simulations also account for that phenomenon?
That's a great question. And yeah, that's one of the things I'm puzzling over right now. But essentially, I think bottom heaviness and top heaviness are probably two independent things that are dictated by different physical processes. It may be possible to accommodate both observations, but I can't say for sure.
Okay. We are out of time. Sorry. We should take it to the coffee break.